this cell goes and sits here, and this sits because that is the anode side. This sits on top, and then the cathode sits on top like that. So that is your cell.
Really?
That's a single. That's how thick it is. So when you have 2 kilowatts, it will be about that height.
There's a whole commercial size and a commercial product. Yeah.
This is a commercial site. 2 of them like that, like this actually. Air in, air out, gas in, gas out. So it goes in like this and goes out like that. So you can see, so the hydrogen comes in here, goes out here. The air comes in here. This is the air side, comes in here, goes out here. We put the seal. The seal is this. This is a demonstration seal. At the moment we have to make this seal a bit thinner, but this is a bit too thick. It's just demo one. The reason why we are saying it, if you look carefully, we have made the design so that the cell sits flat in here. So when you put this in, the seal has to be pretty much almost nothing. Roughly less than 100 microns. The 100 microns allows you to have a what you call a seal that is much more different from the thermal expansion of the metal.
Wow.
If you less than 100 microns, you can have it from 9.5 to 12, where the thermal expansion of this particular metal is 11.5. So you can have that bigger variation, and therefore you can thermally cycle quite happily.
So if it's thinner, it can tolerate.
Yeah. So the thicker the seal, the less the difference has to be. Thinner the seal, the greater the difference could be. Because what we have is this is coated with a glass seal. This particular glass seal is about 10, 9.5, 10. But that is about less than 100 microns. So this is the first iteration. The next iteration is we have developed our own enamel, which is very close to the thermal expansion of this, which you would have seen in the CTE measurements.
Fantastic.
It's called the N21. The N42 is much closer.
Okay.
Just that. And I'm still trying to modify it and make it even better.
And how are you thinking of making it thinner?
It's all to do with design.
Okay.
Because if you see, this is a cell. The standard, if you go into the marketplace, your competition will be Blue Gen.
Yeah.
We want to beat them. I was the one who developed the Blue Gen
Okay.
cell and helped to make it.
Wow.
And this is 400 microns thick. That cell is 200 microns thick. But by designing it, now it is flat as this plate, so the seal becomes very thin.
And what's your ideal thickness of the seal?
Ideal thickness is 50 to 100 microns.
Okay.
You can print the seal, you can tape cast the seal,
Yeah.
but they are all costly and wasteful.
Yeah.
Printing it, bang,
Fantastic.
dispensing it with a robot is
Yeah.
faster, quicker, and it is
Fantastic. Yeah. Very good.
and very clean. The screen printer does the coating on these.
Yeah.
If you want to give a competition, you need to give competition to solid power, and the degradation coating for solid power, the patent is with me. I was the inventor of that coating, and now we have what you call reinvented it to circumvent my own patent, which actually is better because the final product, once you start firing and running it, the conductivity is higher than what they have for the coating. So you are one step ahead. The main thing is wanting to patent that. It is, I think, a very valuable patent. So if you're happy, you can get it patented and you can keep it. You can even sell it to solid power.
18 years before it comes. 18 years.
So that is there, available to for you to buy and patent it from John. and the seal also is there, but we have to test the seal. Okay, any innovation has to be tested and seen long term. For a long term test, you have to run for at least 1 year. The seal sees oxygen on one side, fuel on the other side, and that has to be done, and we have to thermal cycle it and test it. So that is the next
Which means
iteration.
turn it off and turn it on.
Yeah. So and run it long term. We collect the current out from underneath and start testing it. Gas lines will be connected immediately once we do. These are the gas lines which we have flexible for the air side and for the hydrogen side. Because it is only a test station, but they can be made to the size of a bar fridge.
Okay.
So actually, everything can be about the size of this.
Yeah, that's pretty.
So it all depends on the how much of wattage you want out of the whole thing.
That size would be about 2 kilowatts.
This size will be about 2 kilowatts.
Yeah.
And you just leave it outside the house, and you'll get tons of water out of the whole system because
Yeah,
it
that's
produces the byproduct is steam, and heating the house with it because it is superheated steam.
Yeah.
So you can heat the house without using electricity.
Yeah.
So that's where if you look at solid power, they say efficiency of 80%. They use combined heat and steam, 80%.
Yeah.
And that's what I'm doing here, printing plates and coating. Print the cathode
Oh, I see.
and the anode coatings. The reason for that coating is to give it what you call a cushion, so that when the seal comes down and for good contact as well. But the coatings contain the lower degradation additive to it.
Wow.
So it'll be a slurry steel with binders in there, plasticizers
Yes.
and so on. So you just lay it down like an ink, if you like. Yeah. And it will dry, and then you sinter it. Heat treat. Sorry.
Yeah. No. But the coating that goes on this is heated when we put the stack together.
Ah, okay.
So
Ah.
it has got a higher conductivity and all that.
Okay.
So the current collection is more efficient.
Brilliant.
And because it has got the non-degradation additive in it, so that coating does not degrade because of the chromium poisoning.
Got it.
If any chromium is present. So it is that there are about 2 coatings I have to put down on each one of them.
And so that stops degradation, does it, on the anode and
Yeah.
cathode? Okay.
Degradation, and for compliance, when you put it together, there is a slight compliance in there at all times, so that the cell doesn't break in the process.
That's good.
Yeah, it's like a shock absorber. So you can see this was put down because this is mainly for a silver print
Ah, okay.
for getting current collection.
Very good.
So that's where it is at the moment. So it's pretty exciting.
It's very good indeed.
These coatings are done by aerospace coating engineers
Ah, okay.
in Melbourne. So they know what to do, how to do it, what to buy, and what particle size. All that has a effect of getting a good coating.
Mm.
So they know it, and from Melbourne, machined by people who are doing the same thing for solid power as well. So they know exactly, once you give them the drawings, they'll immediately put it and one run and they will machine it. So it is pretty,
Very good.
the technology is there only to put it together. The only difference is the seal and the degradation coating. That's the technology that everybody is struggling with, and I think I'm pretty close to getting it right.
That's the biggest challenge for the whole SFC. Sales
Because
and degradation.
if you look, Bloom Energy has not divulged any of their issues. They don't even say how. All the technologies, SOFC companies have only stated how long they have run it, but in between, how many times they have changed their stacks, they haven't said. But the total running hours they have given. It is actually good, but it doesn't say how many times they had to change the stack to get that total running hours.
Yeah.
At the moment, solid power is running more than 2 years. That's the 2 to 3 years now.
No, less than 2 years.
They can't-
No, they have got some old ones that ran for
Yeah, but
3
the
years.
new product is less than 2 years.
Yeah, less than 2 years.
Because Sofc closed like March 2015.
And
They
they
took it
said-
over like at the end of 2015.
Yeah.
So the operation is less than 1 year. The new product,
The new ones they are making is less than 1 year.
less than 1 year.
They've got the old stock which they bought it in Germany and they put it together. That is running for about 2 years. But they have thermal cycle wise, they have never thermal cycled it except for once they did a trial test for 1 cycle. And that's about it.
You've done 20, haven't you?
No, we should be able to do 20 because it is all to do with the seal being in the right quality.
That's
For
all.
that
Right
ex-
coefficient of
thermal
the,
expansion.
That's our sales is in this. Let's suggest sales in this furnace.
It's
Has been here for many thousand hours now.
now it's 3,000 hours that we have reached.
Okay.
really? And that's what the ceiling's testing. No breakdown or anything.
No, we have to keep it running to age it to see how the seal has changed its CTE, but we have still got a good result out of it.
After 3,000 hours.
Which is 6 months. No, it's slightly less than 6 months. Because it needs a specialized, dedicated, running continuously and come and switch it on and off. So it needs to be, the furnace needs to be, the rest of the system needs to be operational so that it doesn't break down. And I think this furnace won't last long as well. So we have to start buying a new set of
The
furnace.
seal's going to last longer than the furnace, is it?
Yes, and
This
I
is
think that's what is going to happen. So, I believe that the seal at this stage has to be tested, and for the next 6 months or at least, or 1 year, to know exactly what is happening.
Well done.
Fantastic.
That's